Hello everyone, my name is Đinh Đạt Nguyễn and today I'm truly honored to present our work titled Enhancing Class Incremental Learning with Feature-Weighted Parameter Fusion and Feature Alignment. Our work explores how we can improve continual learning using powerful vision language models like CLIF while reducing the catastrophic forgetting that deep learning systems commonly suffer from. In today's talk, I will guide you through 5 main sections. First, I will provide an introduction to class incremental learning and explain the problem of catastrophic forgetting. Second, I'll discuss related works covering traditional approach and more recent click-paste methods. Third, I'll introduce our proposed framework, FPFA, which stands for Feature-Weighted Parameter Fusions and Feature Alignment. Fourth, I'll present our experimental results on two popular benchmarks, Cypher 100 and Tiny ImageNet. And finally, I'll conclude with key finding limitations and promising future directions. At the starting point, let's briefly review the challenge behind continual learning. One of the biggest challenges in deep learning today is that models trained on new tasks tend to override their knowledge of previous learned tasks, and this phenomenon is known as catastrophic forgetting. And you can see on the left side of the picture, the traditional machine learning workflow, we train the models once on a fixed dataset and then deploy it. However, in the many real-world scenarios, data does not arrive all at once. Instead, it comes sequentially. On the right side, we have the concept of continual learning, where the model must continuously incorporate new information without retraining from scratch. But if we fine-tune a model in a naive manner, its parameters shift dramatically, destroying previous learned representations. And this motivates the need for framework that allow the model to adapt while still retaining stability. Several strategies have been proposed to mitigate the forgetting. Regularization-based methods constrain how much the weights can change from previous tasks. Memory-based approach store samples from past tasks, allowing model to rehearse, while architecture-based methods allocate separate parameters for tasks or expand the model and add task-specific modules. Despite considerable progress with these advancements, existing approaches still face bottlenecks such as memory limitations, computational costs, and task interference. Very recently, vision language models like CLIF have emerged as extremely powerful feature extractors. CLIF only learn visual and texture embedding, allowing the model to generalize well even without fine-tuning. However, in a continual learning setup, maybe fine-tuning disrupts CLIF's shared embedding space, causing the presentation drift, misclassification, or catastrophic forgetting. So, we propose a framework, FPFA, address the issues through two main components, the feature-weighted parameter fusion, to protect the important parameters across tasks using the feature information matrix, and the feature alignment, use lightweight adapters for efficient update. Together, these components reduce the forgetting while maintaining strong adaptability. Let's now review some relevant literatures. Because CLIP provides a shared textures and visual embedding space, many recent works explore CLIP for continual learning. Two common strategies include prompt tuning. Here, learnable prompts are introduced to modify CLIP input space, or adaptive tuning. These are lightweight trainable modules to specific layers while keeping the backbone frozen. Despite their efficiencies, these methods still suffer from representation drift, especially when learning semantically similar classes. And this drift can distort decision boundaries of earlier tasks, resulting in forgetting. The next key concept that I want to introduce is the feature information matrix. The feature information matrix is a fundamental tool in statistics that measures how important each parameter is to their predictive distribution. Previous words such as EWC and MAS use feature information matrix to reduce forgetting by protecting the key parameters. It has shown that incorporating feature information matrix can significantly improve the stability by protecting the important parameters. However, feature information matrix has been only explored in the context of clip-based continual learning. So our work leverage the theme not just to regularize parameters but to strategically fuse them across tasks. I will now walk you through the core of our proposed methods, FEFA. Here you can see this is the overall architecture of FEFA. So let me break it down. Both clip text encoder and image encoder are frozen. We introduce a lightweight linear adapter that transforms the image embedding. Each task is trained using a classification loss, a feature alignment loss, and after each task, we compute the feature information matrix. We guide our parameter fusion step. And the framework has two major pillars. The feature alignment. This ensures that semantically similar classes do not collapse into each other. As you can see on the left side of the diagram, that is a part of the feature alignment, and the feature-weighted parameter fusion is on the right side. Ensure that important parameters from previous tasks do not get overwritten. Together, they yield a stable yet adaptive continual learning framework. Now let's dive deeper into the feature alignment. In continual learning, new classes often resemble older classes. For example, wolf, husky, or car and truck may be confused. So to address this, we leverage the clip text encoder to identify the hop pairs, the pairs of class names that are semantically similar. We can compute the Gaussian distance between every pair class, and if the distance is below the threshold alpha, we consider that pair as a hard pair. By identifying these pairs ahead of time, the model can push their representation apart and reduce confusion later. Another challenge is that storing raw training data from past tasks is often impractical due to memory or privacy concerns. So to overcome this, instead of storing image, we extract the clip image embeddings of all classes, estimate their mean and covariance, modeling them as multivariate Gaussians, then generate a synthetic features assembling from these Gaussian distributions. And these synthetic embeddings act as a lightweight memory play, allowing the model to maintain awareness of earlier class without needing the real data. About the loss design, the feature alignment loss integrate pole, real embedding from the current task, and Gaussian sample embedding from previous tasks. This thought is to strengthen class separations to preserve the old class representational boundaries, also reduce the interference between the semantically similar class, and allow the continual adaptation no replay buffer. Together, these design choices address both semantic confusions and feature collapse. Now let's discuss the second pillar of our model, feature-weighted parameter fusion. So, not be averaging a parameter across tasks treats every parameter equally, and this often leads to forgetting. So here, instead, we use the feature information metric to determine how important each parameter is. Parameters with higher feature values are considered more important, more critical. Thus, when moving to a new task, we merge parameters by weighting them according to their feature importance, and this preserves the crucial information from previous tasks while still enable the model to learn from the new task. The fusion process provides several benefits. It preserves the model stability by protecting the high important weights. It still maintains plasticity, allowing adaptation to new tasks. And because we use a diagonal feature matrix, it remains computationally efficient. So this combination give us a stable and flexible approach to continual learning. Let now, let's now move on to the experimental results. Let's now move on to experimental results. We evaluate FVFA onto benchmark datasets, Suffolk 100 and Tiny ImageNet. Each contained 100 class. We use a Cliff VITP16 backbone, a linear adapter, no replay buffer, and use a DAP optimizer with multi-step learning rate schedule. We use a hardware threshold alpha equals 0.25 and a lambda Fisher fusions of 0.5, and we evaluate using the final accuracy, which measures the performance after the last task, and average accuracy, the mean accuracy across all tasks. So here, you can see the numerical results. Across all settings, 5-step, 10-step, or 20-step, FBFA surpassed many strong baseline. And for instance, in Suffolk 100 with FBFA achieved a 74.67% final accuracy and 84.76% average accuracy. This score clearly indicates that FEFA is significantly more stable over long task sequence. Here are the accuracy curves. As the number of classes increase, FBFA maintains high accuracy and declines much more slowly than at LCA, and on Cypher 100, FBFA remains about 80% accuracy even when reaching 60 class. On Tiny ImageNet, the gap between FBFA and SLCA grows larger throughout training. These trends show that FBFA's superior ability to resist catastrophic forgetting. So to conclude, we propose FBFA, a novel framework for class incremental learning that combines feature alignment with separate similar class and preserve class boundary. Feature weighted parameter fusions, which protect important parameters during the continual learning. FPFA achieves strong results across multiple incremental setups and completely eliminate the need for replay buffer. In future work, we aim to scale FPFA to larger datasets, explore the integration with the prompt tuning, extend to open world or zero-shot continual learning, and further improve the computational efficiency. Thank you very much for your attention.